In the previous exercise, we looked at creating a PID controller in Simulink. Now we're going to create PID controllers for 2 heaters on our TCLab, and this will conclude our project. Hopefully you've been able to build up intuition, been able to tie all these concepts together of modeling and empirical models and how they relate to physical models and how they kind of blend together when we fit the physical models to our current conditions. So now we're going to obtain our tuning constants, our constant for gain, integral control, and derivative control, as well as feed-forward control, and create a PID, or 2 PID controllers, I should say, that control heater 1 and heater 2. If I just want to zoom out just a bit and just show our system here has 2 set points where we compare the conditions, the measured PV, so the measured temperatures, and then we change our PID based on the delta temperature between what we want and what we have. With that feed-forward control, we will take into account first KFF1, which is the difference in the measured PVs, and then KFF2, which is the opposite. KFF1 will look at how 1 affects 2, and KFF2 will look at how 2 will affect 1 with the feed-forward control. The feed-forward control will then anticipate the action from the other heater, the heat exchange between the two, and then we'll actually move to the actuator where we'll implement whatever settings from the PID controller we calculated. We then move on to the actual process, which is implementing that within the temperature control lab unit. And then finally we have disturbances, which is this top arrow. The process plus disturbances give us our actual process variable, which is then sensed by the sensor, and then we repeat the process, comparing our measured temperature and our set points. So let's go on. Let's look at our IMC correlations really briefly. If we remember from previous activities, at least my quantities, I'll just write them down here in this code block right here. Let's discuss what they should actually be, and let's actually do it. Here I have the results from our modeling activity, or not our modeling, our estimation activity. If we look at the regress parameters, I had a gain of 0.65, KD of 0.1, tau p of 120, and theta p of 0.16. So I'm going to go ahead, I'm just going to copy these like this. Let's see if I can. Copy output. Right here, Control V. We're just going to go like this. Nope, Control Z. So Kp is equal to 0.65. Kd was equal to 0.1. Tau p, process time constant of the process, was 120, and theta p, the dead time of the process, was equal to 16. Now I'm going to say we're going to keep with moderate tuning. So let's just go ahead and calculate these out so we have an idea. Tau c will be equal to the maximum of tau p, or 8, you had to make sure that was 8 or 0.88, times theta p. And then Kc is going to be equal to tau p plus 0.5 times theta p divided by Kp times tau c plus 0.5 times theta p. Is an unfamiliar keyboard, you can tell. Tau I, like capital I, is equal to tau p plus 0.5, it's an O, 0.5 times theta p, theta p, and finally tau d, we'll do capital D again, is equal to tau p times theta p divided by 2 times tau p plus theta p. So we'll go ahead, I'll smooth this, and this should run everything. So we have our constants, and then our guesses are that Kc should be 1.4, tau I should be 128, tau d should be 7.5. So let's go ahead and let's implement these. We don't have our feed-forward relation, but we'll look at that. So Kc should be 1.4, so much lower. Tau I, 128. Oh, there we go, right on. And tau d, 7.5. We'll say 7 for now. So it definitely is moderate control. You see it's kind of it's not very aggressive, it's slowly going up. And so it's definitely moderate control. Let's try changing our tau c to aggressive control. So aggressive tuning would mean that we just change tau c, and we change it so that tau p, it's 0.1 times tau p, and 0.8. Let's make sure we did that right. Aggressive is 0.1 times tau p, 0.8 times tau p, or theta p, excuse me. Let's also just check, sometimes I find that my taus become thetas and my thetas become taus. This is a theta, tau p plus 0.5 times theta, tau p times theta p, 2 times tau p plus theta p. Cool. Let's go ahead and change this just a bit. Our new Kc is equal to 8.9. That's definitely more aggressive. So we'll just call it 9. Tau I is equal to 128 still. Tau d is 7.5. I like that a lot more. I wonder if we could do better. For example, let's try making our integral control a little bit more aggressive. That changed a bit. Let's maybe make our Kc 8. So a little bit higher of a gain. This number's changing a bit, so let's maybe make it 7. Do we dare do 7? So I think our problem is still the integral control. So I'm going to slowly make that number a little bit lower. And the other thing we haven't implemented yet is that we need some feed-forward control. So let's set that to 0.2. I like that quite a bit, actually, to be honest. I'll just click this. Oh, that's quite a bit lower than I wanted. So you can see how tuning correlations give us a good place to start, and then from that, we're going to slowly work our way to make the performance more in line with what we want. That's the thing about engineers versus just having a calculator. Engineers are there to understand the principles of the system and how to change them in a good way. So here we have our PID. There's a lot more initialized vectors than you may have seen, but there's nothing to be intimidated by. We initialize our time. We're going to go for 600 seconds. Initialize our temperatures, or our y0s, are both 1.0. And then our time vector is going from 0 to the final time with 601 points in between. We have our proportional terms, our integral terms, our derivative terms, feed-forward terms, and our error for each time step. We have the same for the second heater. Finally, we have the controller outputs, the process variables, and the set points. We'll change the set point to 60 for the first one until the end, and then at 400 to the end, we're going to change it to 40 actually. With set point 2, we'll leave it at 0, and then we'll move up to 100 at 150 seconds in, we'll move it to 550, and then 350 seconds in, we'll move the set point to 35. Finally, we have our tuning core. These are the relationships between the two. So KC1 is equal to 2 times KC2. And KFF, K feed forward 1, is going to be KFF. KFF2 is going to be KFF times 2. These are the relationships because the heaters have different powers. And finally, we have IAE, which will track our integral of absolute error. We will connect. We'll set Y0 equal to lab.T1, and as well our PV1 and PV2 equal to lab.T1. It's okay to do T1 for both. We'll actually change this to T2. And then we'll go ahead and we'll record the performance of this system. So go to my live editor. I'll just hit run for everything. We'll make sure things are running. I'll look for a plot telling me that things have started. So we're connecting to the lab right now. And I just saw it light up, so that's a good sign. Just took our time and we're looping. So I'll go ahead and move this out. I'll just look for this plot just to see that we're running. And I see just now that it is set so that it won't run. We won't see it till afterward. So I'll go ahead, I'll let it run, and we'll see you on the flip side. All right, let's take a look at our final solution. You'll notice our integral of absolute error is about what we predicted, 7,160. We predicted in that range. You'll notice that our temperature comes up and reaches, it kind of tapers off as it starts to be a little bit more conservative as it approaches the set point here. And then our heater 2 starts off a little bit higher than we'd like, and so because of that we'll have some jitters as it tries to go down, and that derivative control causes it to kick up once or twice. Nonetheless, it comes up and you can see some sort of it's kind of like bimodal distribution where it starts to scatter a little bit and have 2 different temperature readings. That usually happens because of the power source. What's interesting is I actually have it plugged into a different power source. Usually you see that when it's plugged into the computer. But we can see nonetheless it rises and approaches the set point as well. One thing I would point out is that we notice here on the heater actuator action that both of them have quite aggressive heater action, especially probably due to that derivative control. As we have small changes in the temperature readings, it's still going to cause the system to react to that and try to compensate. So it's going to go up and down, trying to keep it at that set point. But nonetheless, we still have 2 heater PID control. Hopefully this has been informative to you, and let me know if you have any questions.